Okay, we're going to now put our exponential function knowledge to work here, and I'm going to address an exponential function problem that is decently basic. You're asked to build the function, and then you are asked to use the function for a given input to find the output, and then you're asked to use the function with the given output to find the input. Okay? Now, when we do the latter of these, which I will do last, you will need to realize that I'm going to need the log function, which will involve the change of base property as well as just the log property of rewriting an exponential function in log form. Okay, so you should have seen that in class, and hopefully this will be a remodeling of that, plus some older material with regard to exponential functions. So let us take a look, shall we? What we have here is a problem that says, suppose that you have a sample of bacteria in a petri dish that contains about 500,000 bacteria. You treat it with penicillin and it kills off the bacteria at a rate of 30% per hour. Okay, the first question tells us to write an exponential equation that reflects this scenario. Okay, and as I do this, let me go back and reread some key things in the problem. I see that 500,000 is something that I'm going to need. This 30% is going to be involved as well. And just let me reflect now where it says exponential equation. Well, that's something that's going to be of the form f at x equals y, which is equal to ab to the x. And I will say that y is going to be my population, so I might use p if I change the notation. A is going to be the initial value of the population, the starting point. B will be the multiplier. And x will represent time, so I might use t if I change the notation. And it is going to also represent, more importantly, the number of changes in the population. And that is pretty much a one-to-one thing because it says per hour. So if I plug in 10 hours, it also means that there were 10 changes in the population. Okay? Well, I see here also that it says kills off. Well, that means it's 100% minus this 30%, which is going to give me 70%. I need to use the decimal form of 70%, so I will say that 0.7 is the multiplier. Again, a multiplier's job is to tell you what part of a population or account balance is remaining. So I'm not interested in the 30% because that's the part that's gone. I'm interested in the 70% because that will tell me the part that's remaining. Okay, so from there, we will write our exponential function. I'm going to write it two ways. I'll write it once with y and x and once with a better notation. If I use y and x, it's just going to be simply y equals 500,000, the initial value, times 0.7, the multiplier, to the x, which I said would be the time. A little more appropriate, a little more mature, would be to use function notations that say the population at a certain time, measured in hours, is equal to 500,000 times the multiplier of 0.7 to the t, as long as t is a time that is in hours. Both of these are completely legitimate. I prefer the function notation one because it has a little more context using the notations of the population depending on the time, and it's just a little better. Okay, so how many bacteria are in the dish after 4 hours? So how many bacteria? You're asking for a population. In the dish after 4 hours, you're given a time. So we know that t equals 4. This question quite simply is asking us to compute p at 4, which means to plug in 4 for the input and state the output. Very basic function skill that you should have, just function evaluation. I'm plugging it in, getting 500,000 times times 0.7 to the fourth, which I just go to my calculator for. So 500,000 times 0.7 to the fourth, and we see that gives me 120,050 bacteria. There's no rounding recommended in the directions, so I'll just write that. Okay? Writing the unit of what that number represents makes sense too, to say it's a number of bacteria. Now it says how long will it take for the bacteria to reduce by half. Okay, how long will it take is implying I'm looking for a time. So t equals question mark. The bacteria to be reduced by half, well, that's sort of telling me a population because I knew the population started with 500,000. So I guess the y is going to be 250,000. Okay? I guess the p at t, I could say, the population at a certain time will be that. So what I'm going to do is I'm just going to take that 250,000 and plug it into my function for y. Okay? So when I set that up, it's going to look like this. 250,000 is equal to 500,000 times 0.7 to the t. Now, I need to get t by itself, and you notice that t is in the exponent here. So we're going to need the inverse of to the exponent, okay? And that is going to involve log. And you should have some sense of how to move from an exponential format to a log format in watching this video. Okay, so to get t by itself, my first maneuver is to divide by 500,000. And do that on both sides. And interestingly enough, it just gives me 1/2, which makes sense because I was finding where the population was cut in half, is equal to 0.7 to the t. Now, from here, I will need to rewrite this in log notation. This is exponential notation because if you notice the variables in the exponent. Okay? So I'm going to rewrite that as a log, and I'm going to write log base 0.7 to get 1/2 is equal to t. Okay? That's just rewriting exponential to log form. Now, it seems here if I could just compute log base 0.7 to get 1/2, I'm done. And I can do that on my calculator as long as I change the base. If we notice here, the base is 0.7, but my calculator only does log base 10. Okay? So I'm going to have to change the base from 0.7 to 10. Well, the change of base formula is something you should have seen. It just says, well, if you have log base b to get a, you can rewrite it as log a over log b. Now the base, which is not written here or here, is 10 when we don't write it. Now why is it great to go to log base 10? Because again, that's what my calculator does. Okay? So I'm going to use this format and rewrite this expression just quite simply as log base 10 to get 1/2 divided by log base 10 to get 0.7. Now from there, I just simply go to my calculator, which I'll move out of the way so you can see it. Okay, I'm going to hit my log button. Again, it's base 10 because that's all my calculator knows, of 1/2, or to get 1/2, divided by log base 10 to get 0.7. This gives me a t that is equal to 1.94 approximately. Okay? This is my time in hours, but if you notice, it says round to the nearest minute. So I'm going to have to convert the fraction of an hour to minutes, and to do that, I just say the 0.94 times 60. It's going to count as 56.4 minutes, so saying to the nearest minute, it's going to be 1 hour and 56 minutes. Excuse me, I spelled hour wrong. 1 hour and 56 minutes. And at this time, it should in fact create a population of 250,000. Now, if I wanted to check that, I guess I could take the function and just plug in 1.94 and see if in fact it gives me the appropriate population of 250,000. So I'll do that now, just kind of freehand here, and I'll say I'll start with 500,000. And I will use a multiplier of 0.7, raised up to the 1.94, which I rounded. So it's not exactly going to be 250,000, but it looks really, really close. Okay? So it just goes to show you, too, that this exponent is very sensitive. That little bit of rounding I did actually, changed the population by, it looks like 300 people. Okay? So, um, I think this is close enough. The log answer is decently accurate, and it is what is allowing us to be able to solve when you have a variable in the exponent. So I hope you enjoyed this. It's a pretty comprehensive outlook on how to use an exponential function. Very much just kind of build the function, use it forward, use it backwards. Enjoy.